Hey students, how we doing today? That's just great. I'm doing the same as you are. All right. So I'm going to go through in-class assignment 9.5. I'm just kind of going to do it as I go along. Hopefully you have the assignment in front of you because I'm not going to write down what all the problems say. So have the assignment in front of you, and I'll go through this step by step. So number one, 70% of all high school students buy their lunch at their school cafeteria. Suppose we will sample 500 high school students. So part A, define the parameter and population of interest. But actually, before I even answer that, I want to clue you in on how this problem's set up and what we're looking for here. Problem one here, we're going to be looking at the sampling distribution of p hat. And why do I know this? Sampling distribution of p hat. Why do I know this? Because number one, I'm given the real proportion. I'm given the actual value of p, 70%. And also, we will sample 500 people. So n is going to be 500. We're going to sample 500 people, but we don't know how many successes. So we're going to be looking at the sampling distribution of p hat. All right, so define the population and the parameter of interest. The population is going to be, in this case, all high school students. Because what are we looking at? The proportion of high school all lunch. I'm actually hungry for lunch. All high school students is the population. And the parameter of interest, we actually know what the parameter is. Let's remember what the definition of a parameter is. It's a numerical value that describes a population. Well, is there a numerical value here that describes the population, or is there an unknown numerical value that describes the population? Well, there is a numerical value that describes the population. It's 70%. It's the 70% of all high school students who buy their lunch. And you could even be more specific here, and we know that the actual parameter, p, because remember p is the parameter, it's the true proportion of, in this case, all high school students who buy their lunch. Part B, does this follow an approximately normal distribution? Hopefully the answer is yes. Let's find out. We got to check if NP is greater than 10. And n1 minus p is greater than 10. Well, we will sample 500 people. The probability of success we're assuming is 0.10. That should be 350. Last time I checked, that's greater than 10. And then n1 minus p, or the probability of failure, is that greater than 10? Well, that's 150, and last time I checked, 150 is greater than 10. So the answer is yes, it follows a normal distribution. Part C, what is the mean and standard deviation of the sampling distribution? Well, let's remember what the formula says. It says that mu of p hat equals p. Well, what does that mean? Again, and in this case, that's going to be that the mean of all sampling proportions is 0.7. That is, if I took like many thousands and thousands of different simple random samples of 500 people from the population, on average, I'd get 70% of people would say they buy their lunch on average. And what about that standard deviation? That is going to be this formula, which hopefully is going to work its way onto your formula sheet. Hint, hint. So that in this case is going to be 0.7 times 0.3 divided by 500, which, let me put that on my calculator. That's 0.0205. So just before we answer part D, E, and F, let me again just kind of do a recap here and let's see where we're at. So this follows a normal distribution. The sampling distribution of p hat follows a normal distribution. What is the sampling distribution? This would represent the proportion, the percent of people in samples. If I'm always sampling 500 people, if I took thousands and thousands and thousands of different simple random samples from this population, I would expect, as I said, on average they would be 70. That 70% of people would buy their lunch, and with a standard deviation, what we calculated before there, about 2.05%. In other words, if I added a standard deviation, let me put this down here, that's 0.7205, and if I took one, I'm gonna just slightly round these to make my life easier. I'm gonna slightly round this to the standard deviation to 2%. So if I kind of took away a couple standard deviations and added a couple standard deviations, again, I like to put stuff in perspective. What this would mean, about 68% of the time, if I were to take thousands and thousands of different samples of 500, about 68% of the time, I'm going to get between 68 and 72% of people say they buy their lunch. And 95% of the time, I'd get between 66 and 74. And if I even take one more standard deviation on both sides, nearly all, 99.7% of the time, I would expect between 64 and 76% of people in my samples to buy their lunch. So again, this is called the sampling distribution of p hat, and this is such an important part of statistical inference because it kind of represents all the possible outcomes, the likely possible outcomes of my sample proportion. In this case, if I'm always sampling 500 people, again, I would expect, for instance, and about 99.7% of the time, nearly all the time, I would expect between 64 and 76% of people to say they buy their lunch. So if I get something like 80%, I'm going to find that extremely unusual. There's something going on with these unusual events. Either they're caused by random chance, in which case it would be very unlikely that they're caused by random chance. Usually there's something going on. And when we do hypothesis testing, a lot of times we're going, well, maybe this assumption was wrong to begin with, and that's the null hypothesis. But again, we'll cross that bridge. We're not at that bridge, at least with this problem yet. Okay, so part D, what's the probability that 75% or more buy their lunch in that sample of 500? So there's a couple ways I can do this. I could just use the mean and standard deviation of that bell curve. In fact, maybe I'll do this both times. So we're looking, it had a mean of 70%, 0.70, and the standard deviation again was 0.0205. So if I do it this way, this might be the most direct way since I already know the mean and standard deviation. I can just normal CDF in the calculator. And normal CDF, my lower bound would be 0.75. I'm going 75% or more, so off to infinity. The mean was 0.70, and the standard deviation was what I had found there before. That's one way I can do it. I can actually also use that formula for that test statistic. If you recall, this formula says p hat minus p naught over p naught 1 minus p naught over n. And what this is going to just find is it's going to find the z-score. How many standard deviations is this 0.75 from the mean? Well, we have 0.75 down here, 0.70 here, and this is going to be on the bottom, 0.7 times 0.3 divided by 500. And if I do that, I get 2.44. That my z naught equals 2.44. And then what I can do with this is my z-score. So to find the probability, I can go on my table. As I had mentioned, by symmetry, I can actually just take the negative value here as well and go into my normal table. I'm looking at negative 2.44. And I got 0.00, this is going to be my final answer here, 73. And that's with the z-score. I'm going to confirm using that normal CDF here that I get just about the same answer. And again, if your answers are off by a little bit, I'm going to look at your work. And if it's just a rounding mistake or something like that, it's not going to be an issue. If you're off by, a couple, not a whole percentage points, but a couple hundredths of a percent, no big deal, right? And if I actually, because good point, case in point here, I went up here and I did this this way. And, oh, wait, what did I get here? Yeah, I got something extremely similar, but actually if I rounded this, I would have gotten 0.0074. Is there a big difference between this answer and that answer? Not at all. Both are just fine and dandy. All right, so part E. This is a good point. If if you feel comfortable, pause the video and try the next one. What's the probability that 60% or fewer? So this is going to be p hat is less than 60. Again, we're using that same bell curve. There's a bunch of ways of doing this. I'm just going to normal CDF this at this point. So I'm looking for less than 60%. And again, I'm going to normal CDF this in my calculator because it went a little faster than the z-score. So I'm looking fewer than 60%. So that's going to be from negative infinity off to 0.060. The mean was 0.7 and the standard deviation was 0.0725. So if I do that on my calculator, I got... Oh, my phone's ringing. Somebody's popular. And I got a pretty small answer, 5.36 times 10 to the negative 7. So to answer part F, a student finds that 60% of his students buy their lunch in her sample. Is this unusual? And yeah, it's unusual. Yes, since by random chance, since this has a 5.36 times 10 to the negative, fifth if I move the two decimal places over, percent chance of happening by random chance. Chance of happening. And again, by random chance. Maybe there was something wrong. Maybe the sample wasn't random. Maybe the sample came from her school. So maybe in reality, in her school, that less than 60% of people bought their lunch. All right, let's go ahead and look at problem numero 2. That's Spanish for problem number 2. Okay, that wasn't Spanish. That was Spanglish for number 2. All right, so the makers of Fruity Yum Yum cereal have created a new product called Yummy Yummy Snack-a-Time. They're interested in determining what proportion of kids under 10 like the new product. Okay, so problem A, all right, here's the deal with problem A. The CEO asked for a random selection of kids across the whole country. Why is random selection important? Okay, I'm not going to put this one on your test this time, but next time, absolutely. Why is random important? Random selection means our results are unbiased. And unbiased doesn't necessarily mean it's deadly accurate. It doesn't mean that, if I take a random sample of whatever 500 kids, it doesn't mean that I'm going to be like spot on because it's random. But what it means is that, let's just say it's equally likely to be like too high as it is too low. And we're going to just hit that one up a little bit harder next chapter when we talk about biased and unbiased estimators. But random selection is really important. If it's random, it's not going to favor one direction over another. If it's random, I'm equally likely to have like too many kids who really like Yummy Yummy Snacky Time versus like very few kids who like Yummy Yummy Snacky Time. Okay, part B. Suppose that the company takes a simple random sample of 1,200 kids and find that 832 like yummy, yummy, snacky time. Construct a confidence interval 95% for the proportion of kids who like yummy, yummy, snacky time. Snacky time. All right, so let's start with our sample proportion. That's the 832 out of 1,200 kids who like yummy, yummy, snacky time. And I got 0.693%. So the our critical value of z, this might be a good one to remember, 1.96. As I said, 95% confidence is probably the most common confidence interval. So if there's, maybe a couple that you might want to write on your formula, it's for 95, 90, or 99%, the z stars. So we're going to have p hat plus or minus z star times the square root of 0.693 times 0.307 divided by our sample size. What did I just do there? I was supposed to say p hat 1 minus p hat over n. So I'm just going to go ahead and then erase all my numbers and I'll put them in here in the right place here. So this was going to be 1.96 and this was our 0.693. So before I do anything, I'm going to calculate this margin of error there on the right side. Remember, this is our estimate. That's our estimate. And this is our margin of error. So let's find out what our margin of error is. I'm putting this in my calculator. Alright, it was down to 2.6%. So I can add that on one side and I'll have 71.9, and I could take it away on the other side and I got 0.667. So again, I'm 95% confident that the true proportion of kids who like yummy, yummy snack time, and I'm doing this part C right now. I'm just going to verbally say it. So part C, we are 95% confident that the true proportion of kids who like yummy, yummy snacky time is between 66.7% and 71.9%. So that was part C I just did there, and I said it. Now, I'd mentioned this in class. You don't have to remember those verbatim. Like I'd asked you to memorize those in the notes. You don't need to memorize them, but know them when you see them. And just understand, what are we trying to do with this confidence interval? We're trying to find out, we really want to know what proportion of kids like this yummy, yummy snacky time. So I don't know exactly, but I'm pretty sure, how sure? I'm 95% sure that it's between 66.7 and 71.9%. So part D asks, suppose that the CEO wants to estimate with 95% confidence the proportion of kids who like, supposed to say who like yummy, yummy snacky time, with a margin of error of 0.05%, plus or minus 0.05%. Using your sample proportion from part B as an estimate for P, what is the minimum sample size needed? So you had this formula, and hopefully I remember it myself. Z star squared times P, or P hat, whichever one you have, 1 minus P hat over the margin of error squared. Okay, so N is going to be at least or greater than, okay, the Z star, that's 95% confidence, so that's 1.96. We're going to use the result from part B as an estimate, so that was the 69.3. And if we didn't have an estimate, if I didn't have anything to go off of, what would I use for P? What? I didn't hear you. You're supposed to answer that question. What am I supposed to use for P? That's right, 50%. So if I didn't know, but I do know now, if I didn't know, I would use 0.5 times 0.5 for these two here, for those two, because that's going to maximize my margin of error. And don't forget, with this 0.05%, we got to write that as a decimal. So it's not 0.05, it's 0.005 squared. So now we can take this fancy-dancy formula, put this in the calculator, and 0.005 squared, and I get 32692.16. So I have to sample at least what? That's right, I got to round this up. I got to sample at least 32,693 people. These are people, right? These are kids. These are kids under 10. All right. I want some yummy, yummy snacky time right now. All right, part E. How much larger of a sample size would be needed to reduce the margin of error in half? Now, all right, so I'm going to show you how to do this without actually having to put any numbers in there. So, whatever my z value, star value is, that's not going to change. Whatever my p-value, my p is, or probability of success, that's not going to change. That's not going to change. But if I'm saying to take this margin of error, remember we have to square it? But if I wanted to see what would happen if I take this in half, so I'm going to take half that margin of error and square it. And what does that mean here? So I'm just going to leave the top. I'm going to call the top whatever it is. You'd multiply all those numbers together. Let's say it's x, and then this 1/2 is going to get squared, which is going to be 1/4. So what I get here now, I got a complex fraction. To get that 1/4 out of the denominator, I could multiply the top and the bottom by 4. I'm going to get 4 times x over the margin of error squared. And again, if I didn't have this 1/2, where was this? Whatever this was, as I said, is going to stay the same. And you could think initially I would have had, this margin of error. What does that mean? To actually to cut that margin of error in half, I have to actually increase my sample size by a factor of 4. There are a couple ways you could have done this, but the idea is I need 4 to reduce my margin of error in half. This is always going to be the case. I need at least 4 times the original sample size. So whatever I needed before, at least 4 times the original sample size. So for example, going back to my result before, when I got this margin of error 0.005, I needed 32,693 people. I would at least need that many times 4. So in this case, 130,000. So specifically to answer that last question, I need 130,772 people to cut it in fourths, to cut the margin of error in half. Well, now, how much more of a sample size would I need to reduce the margin of error by 1/4? So let's see the same thing, and n is going to be, I'm going to do the same thing. I'm going to take that z star squared times p, 1 minus p, and now I'm looking to take this margin of error and break it down into fourths and square it. So when I do this, I got to square that 1/4. Oops, that's a square. P, 1 minus p, and now I got 1/16 times the margin of error squared. And again, got to multiply top and bottom. And I got 16 again. I'll call that the regular margin of error, whatever I had there before. All right, so long story short, I'm going to need 16 times the sample size to reduce the margin error in fourths. So there's this nice little rule that we get from this. You notice how before we had cutting the area in half, I needed 4 times the people. Now to cut it in fourth, I need 60 times the people. In other words, I could take, like, if it's 1/2 and I can square that, and that's how many more times people that's how many times more people I would need. Okay, number 3. Looks like we're going to do a hypothesis test here on number 3. Across the country, 23.2% of drivers have had a traffic ticket in the last 2 years. You suspect that teenage drivers have a higher rate of traffic tickets than the national average. So you take a simple random sample of 732 teens and find that 202 have had a ticket in the last 2 years. Is there convincing evidence that teens get more tickets at an alpha equals 0.05 level? Okay, so let's state the null and alternative hypothesis and define our parameter. So the null here, we're going to assume it's true that 23.2% of teens have had a ticket in the last year versus the alternative, and again, I like to put that H1 as opposed to the HA, especially with this stylus that I'm writing on, because you can see how that my H0 there looks pretty bad as it is. So again, the hypothesis here is that we get more than 23.2. That's supposed to be a 3. All right. Where P, this is the defining the parameter part. What does P mean? P is the true proportion, the overall proportion, the actual proportion, the population proportion, the true proportion of teenagers with the traffic ticket in the last, ticket in the last 2 years. Again, I'm being very specific here. Why is P not the true proportion of all people who have had a ticket in the last 2 years? Because that's not what we're looking at. We know that. We know that 23.2% of all people had the ticket, had a traffic ticket in the last 2 years, or at least we're given that. We're trying to find the proportion of teenagers in this case. So that's what makes this just a little different. All right, part B, what would a type 1 error be in context? So a type 1 error is when we reject the null hypothesis and it was true. So we reject when this was true. So let me do that again. Excuse me. We reject the null hypothesis when it was true. So we reject this. So this was true. Let me put it this way. Let me erase all these marks here. So this was true in reality, but we conclude this. So we conclude, so this is where we conclude, type 1 error would be we conclude that more than 23.2% of teens get a ticket. When in reality, and I'm usually looking for those words, the words conclude and the reality. When in reality, only 23.2 or thereabout of teens have had tickets. So that's my stylus. They're looking pretty rocking there. So again, you could think that type 1 error is kind of like convicting an innocent person. You're innocent. The null hypothesis was true, but we've come to the opposite conclusion. So it's like convicting an innocent person, if that helps you or not. It's like we've come to this conclusion, when this was really true in reality. The null hypothesis there is true. So if that helps, see if you could do answer C. What would a type 2 error be in this context? So a type 2 error would be, uh-oh, bell rang. I'm going to have to finish this after school. Okay, so the bell has rung. I can't be tardy to my next class. All right, type 2 error, part C. What would a type 2 error be in this context? Well, remember, let's take a look at the definition. A type 2 error is when we fail to reject the null hypothesis when, in reality, the null hypothesis was false and the alternative was true. So what would that mean again, looking at our hypotheses? That would mean we would come to this conclusion, HO, when this was the reality. So we would conclude, a type 2 error would be, we would conclude, I should write a complete sentence there. We would conclude, I'll put that E back, there it goes. We would conclude that 23.2% of teens have had a traffic ticket. I'm just going to call it a ticket. And again, in the last 2 years, when what? When in reality, more than 23.2% of teens had tickets. Ugh. In the last 2 years. I'm being a little specific here, but you know, the variable, what are we measuring? Not the percentage who had tickets, but in the last 2 years. Hopefully that applies to all teens, right? Considering you haven't been driving for very long. Again, a couple things I'm looking for with these type 2 errors. Number one is what you concluded. Number 2 is what reality was. Again, what the point of this when we're doing this hypothesis testing is we don't necessarily know whether the null hypothesis is true or false. So we don't know if we made the right decision or not necessarily, but we can at least evaluate, what would happen if, for instance. All right, part D, check the random, normal, and independent conditions. Random, yeah, it was an SRS. A simple random sample. Normal. NP and N1 minus P should be greater than 10. I think we're getting used to this hopefully by now, but N again was 732. P was 0.232. Check to see if that's greater than 10. And for time's sake, I'm going to let you figure out the rest of this by yourself. I think you can do that. I know with the independent condition, this has traditionally been a few more questions. But there's really two things about the independent condition. One is the 10% condition. I'm going to let the 10% condition slide on this test. You don't need the 10% condition for Tuesday and Wednesday's test on Chapter 9, but you will for the next one. But the other part of the independent condition is it's each individual observation independent of another. And we would assume, since these are random samples, we would assume that each observation is independent. I think that's good enough. And again, what do we mean by each observation is independent? That if the first person in my sample had a traffic ticket, that should in no way influence whether the next random person in my sample has had a ticket or not. Shouldn't have any bearing, right? No, it shouldn't. Good. You agree with me? No, you don't? Why don't you agree with me? That's fine. You could think for yourself, but I'm just telling you. You know, just saying. All right, part E, let's calculate the test statistic and find the p-value. So part 1 of the test statistic is let's find our p-hat. And our p-hat, we had that 202 out of 732 people had tickets. So let me get a decimal number for this. By the way, I'm not in my classroom anymore. I'm now officially at home. So if you hear my cats in the background, they're already making noise, but you probably couldn't hear that. All right, so this is our formula for the test statistic. And our p-hat was 0.76. Our p-naught was 0.32. That was my cats. Okay. Times 0.32 times 1 minus 0.32, which should be 0.768, if I did that in my head right, divided by 732. And let's see if you can calculate that. I'm going to pause the video and do it myself. Okay, so I got a test statistic of 2.82. This, my friends, is the test statistic. What is the test statistic? That represents how many standard deviations away my result is from the norm. If we looked at, for instance, the sampling distribution of p-hat under the null hypothesis, that is, if the true proportion of kids, teens, I should say, really has a 23.2% chance of getting a ticket, then the standard deviation of this, and I should say that this is the mean of p-hat. The standard deviation is the denominator here. I'm not exactly sure what that is. Like we can calculate it, but the idea is we would expect on average, if it's true, the null hypothesis, that 23.2% of teens have a ticket. Then here's my sample result. I got 27.6% of teens in my sample who got a traffic ticket. So I can use the sampling distribution. Again, it would have a mean of the real proportion or the the hypothesized proportion, and it would have the standard deviation, as I said over here. So what this value represents, the test statistic of 2.82, this is 2.82 standard deviations, in this case, greater than the mean. So my p-value is going to equal the probability that z is greater than 2.82, and why greater? Because the alternative hypothesis was greater. Do teens have a higher percentage of tickets? So if we go to the normal table, we could just line up negative 2.82 since this is greater than 2.82, or we could do 1 minus the positive value on here. If you wanted to, you could also use your normal CDF. The normal CDF here, if I'm drawing this curve, I'm looking at the Z curve. The Z curve has a mean of 0, and it has a, so the mean of Z is 0, and the standard deviation of Z is 1. And I'm here 2.82 standard deviations to the right. So I can normal CDF 2.82 off to infinity. The mean was 0, standard deviation was 1. Either way, I should get a p-value of 0.0024, give or take. If you've got something just slightly different, no big deal. Just make sure you're using at least 3 significant figures in all your calculations. So that's my p-value. What does my p-value represent? What does my p-value mean? My p-value means if the null hypothesis is true. Therefore, if 23.2% of teens have a traffic ticket, then getting a result like I did in my sample, getting something this high, 27.6% or higher, the probability of that is 0.24%. So when I get to my decision, again, that's extremely unlikely to happen if the null hypothesis is true. Therefore, I'm going to come to the conclusion that the null hypothesis is not true. So my decision, and I want to mention that since my p-value is less than alpha, that is, again, 0.0024 is less than 0.05, we reject the null hypothesis. That is my decision. So what does this mean in context? I like to put this little that is to kind of like say, haha, this is what I mean in non-math speak. That is, there is convincing evidence. Hey Pookie. Hey Pookie, what does a cat say? What does a cat say in China? Meow, 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 meow. Okay, he's too shy. He's too shy to speak. So there is convincing evidence that that teens have a higher proportion of traffic tickets. Or you could say that there's convincing evidence that the teens who have a traffic ticket in the last 2 years is higher than the national average in the last 2 years. Again, I just want to make sure of a few things here that you kind of see this here. That when I make this decision, this is about the null hypothesis. Either yay or nay on the null hypothesis. Again, you're kind of choosing one over the other. So in this case, I say I'm rejecting the null. And even if I were to fail to reject the null, I would say that here. And then here, this conclusion, I'm talking about the alternative hypothesis. So I'm saying no to the null hypothesis. It means yes to the alternative hypothesis. And the alternative hypothesis is that the traffic tickets are higher. Okay, we're almost there, guys. I can't believe you sat through almost 45 minutes of me talking. And you had to wait till the last 5 minutes to hear my cats. Who would have thought? Last question. Suppose that in reality, teens do not get tickets significantly higher than the national average. Did you make the correct decision? Commit a type 1 or commit a type 2 error? Well, we came to the conclusion that they do get higher ones. Well, suppose that in reality they don't get higher. So what does that mean? That the null hypothesis was true. That was the reality. What conclusion did we make? We concluded H1. That was our conclusion. We made the wrong conclusion here. We didn't know that, but that was random chance. We committed a type what? We committed a type 1. You got it. Error. And that's what we did. We rejected the null hypothesis when the null hypothesis was true. Type 01. There we go. All right. Yeah, that concludes in-class assignment 9.5. I hope you found this a smashing little video. You can like it. You don't have to like it. I'm kidding. I don't really go by likes. All right, guys. In conclusion, do my kitties want to say anything? No? They're just looking at the video screen right now, awkwardly. They're a little shy. Did you want to say anything to them, Noche? Huh? You want a cat massage? Pookie, did you want to say anything? No, they're too shy. All right, guys. Thank you. Bye.